Mark and many, many other DuPont Central Research colleagues worked on a very, very large project to bring a commodity chemical from initial metabolic engineering, basic science, to commercial reality. And today, Mark is going to describe that effort. And the title of his talk is Moving from Oil to Bioderived Chemicals, a Success Story. As a final note, I wanted to tell you that if you would like to re-listen to this presentation, it will be recorded and either yourself or friends can listen to it. And it'll be available soon. And with that, I'd like to present Dr. Mark Hemtage so he can give his talk on the success story of moving oil to bioderived chemicals. Mark, please take it away.
Thank you, Keith. In the spirit of the Science History Institute, this will primarily be a history lesson about what I think 1,3-propane-diol was kind of in a unique situation in time and location to enable it to be one of the first commodity chemicals made by a genetically engineered organism that was economically better than oil-based production. So my talk will be basically broken down into a short historical background to give you an idea of the potential value for 1,3-propane-diol as a commodity chemical. But the bulk of my talk will focus on the metabolic engineering efforts that DuPont undertook from roughly 1996 to 2002 in developing this organism to make 1,3-propane-diol. It's a story about genetic engineering, protein engineering, and serendipity that led to being able to produce something that was economically, or let me phrase that, produce a metabolically engineered organism that met economic titers, rates, and yields in fermentation. And then I'll end by doing a short follow-up on the commercial production of 1,3-propane-diol to now. So, of course, most of you know that DuPont has a long history of introducing new polymers, basically a century of doing that. DuPont invented, polymers such as neoprene, nylon, Teflon, Kevlar, and they, developed, multiple businesses of engineering various fibers and polymers to make a variety of products. So we had a long history and know-how and technology around polymers. And what we call Serona, the trade name Serona, 3GT, which we'll talk about in a minute, was one of the last of those line of polymers, because now DuPont, of course, has a much smaller presence in the polymer business. So why 1,3-propane-diol? What's unique? Well, let's start with polyester, or PET, also known as 2GT. So that's basically a polymer of ethylene glycol and terephthalic acid to make a polyester PET used in plastic water bottles and a variety of apparel. So Serona 3GT, also known as PTT, is basically substituting 1,3-propane-diol for ethylene glycol. And you're making the same type of polyester, except it has an extra methylene group. And that extra methylene group has a very important impact on its properties, which we'll talk about in a second. And one of those impacts is it makes a fiber that can compete with properties with high-end uses of nylon 6,6, which was one of DuPont's longest and biggest businesses at that time. So let's look at one of the properties that makes it look so good. So this is a chart of stretch recovery for flat yarns. So basically you apply a certain amount of strain to a fiber and see how much elastic it goes back to its original length. And both DuGT and nylon 6,6 have okay properties, but if you look at 3GT, it has significant stretch recovery at higher strains, and it's approaching lycra in its stretchability. And this comes from the fact that extra methylene groups gives a natural kink to the polymer. So it gives this natural ability to stretch and recover completely. So this is a very attractive property. Also, once the fiber's made, it has a soft feel. It's naturally stain resistant, so it has a lot of properties that allow it to compete with nylon, say in the carpet business. So these are the products that have been made with BioPDO. That's the product name that we make from fermentation. So again, the polymers for carpet fibers, textile fibers through Serona, the polyols, which is basically making polymers from 1,3-propionediol itself, making high density fluids, serenol. And then I think that's my understanding is Serenol is probably a small business at this point, but the PDO itself works as a very good substitute for glycols in cosmetics and personal care. It can also be used in detergents, de-icing fluids, and antifreeze. So this is a substitute for glycols that's totally bio-based. So Zymea, as for cosmetics, and Zotera for other applications, has been a very big market for this product. So let's take a look at how this all got started. So DuPont actually was aware of 3GT properties as a fiber all the way back starting in 1946. But and they looked at PDO production from oil and never was able to come up with a competitively economic methodology to generate PDO or produce PDO that would allow it to compete with things like nylon. Then in 1993, Degussa developed a more economical route to PDO from oil. And in 1994, Shell announced Cortera 3GT to replace nylon. So of course, this got the ball rolling because the DuPont nylon business saw competition here. It was going to affect their nylon business. So they knew they needed to get involved with 3GT. And just by happenstance at that about same time, the biotech, couple of the biotech managers in the DuPont Central Research where I work, we're going around the various businesses looking for collaboration opportunities between biotech and the businesses where biotech could solve some of their problems. And they learned about 1,3G or PDO. They learned about PDO from DuPont nylon and knew that PDO is actually a natural product. There are certain organisms that will make 1,3-propionediol. So they saw a potential research project there. And the nylon business bought into that. So they started supporting the research. So in 1995, the first BioPDO was isolated at DuPont. And we knew very quickly this was going to be a long-term major metabolic engineering project that DuPont itself did not have enough expertise. So we brought on Genencor International on partner. They were a biotech company that was a spin-off from Kodak many years before that. They were successful in the industrial biotech area. They were producing enzymes for the ethanol industry, so they knew the cornstarch business fairly well, and we were going to be using that as a feedstock. So it was a good partnership. But at the same time, the nylon business, being a chemical business, didn't have a lot of faith in the final outcome for a bio route, so they started developing the chemical route. And they made their first 3GT from using the Degussa PDO in 1996 and spun their first carpet fiber. And they started production of 3GT in 1997. But this, that was very useful actually to the bio research side of it, because the chemical having the chemical route to 3GT allowed the business to develop the technology, the spinning technology, and the market for that fiber, while it gave the bio route more time to develop the biocatalyst. So by 1997, we had a broad bio-PDO patent to generate PDO from a single organism. The DuPont nylon business opened a PDO plant with Degussa in Germany in '98. We made enough success in the biocatalyst side of things that we made a collaboration with Tate and Lyle, a big large-scale fermentation company for plant production of bio-PDO. And Serona was launched with chemical PDO in the year 2000. So by 2002, we had achieved a commercial bio-PDO performance in a pilot plant. Mohawk Carpet started in 2004, and we built with Tate and Lyle, we built a 100 million pound per year bio-PDO plant in Loudon, Tennessee. And because the PDO we were producing there was more economical and much cleaner more pure, I should say, was a pure 1,3-propanediol than you can produce in the chemical route. Shell could not compete with the Serona bio-based 3GT, and they went out of business in 2009. So why a bioprocess? The Degussa process starts with propylene, isolated from oil to make the PDO through a variety of catalysts. The bioprocess starts with cornstarch sugar and goes to PDO through a single organism. So, with the standard bioprocesses where it's using renewable resources, it has a smaller environmental footprint. Cornstarch in the US is a more reliable feedstock, and we can make a higher purity PDO for polymerization, or more effective polymerization. So the natural organisms that make PDO, it's really to start with sugar, with glucose, really requires two organisms. So yeast, some yeasts under anaerobic conditions will convert glucose to glycerol, and glycerol is a byproduct. And other bacteria, such as Klebsiella pneumoniae, will take glycerol as a carbon source and make PDO. So in principle, you could do this with two organisms, but in reality, an industrial process really requires a single organism. So that requires some metabolic engineering of a host microbe. So let's look at what we're doing here. So what is yeast doing? So yeast is taking glucose, a 6-carbon sugar, and through glycolysis is breaking it into two 3-carbon units, dihydroxyacetone phosphate and glyceraldehyde 3-phosphate. And the gap feeds into the biosynthetic pathways to make cell mass. In an anaerobic process, it is also generating excess reducing equivalents in the form of nicotinamide adenine dinucleotide. And it needs to dump these to keep a redox balance, keep the cells growing. It needs to dump these excess reducing equivalents. And through evolution, it developed a pathway to take dihydroxyacetone phosphate and dump those reducing equivalents there to make glycerol. And then glycerol is transported out of the cell. In a similar fashion, glycerol, as a substrate for Klebsiella, it takes glycerol as a substrate and basically bifurcates the glycerol. Half of the glycerol, it'll oxidize to DHAP to lead to cell mass and growth. It generates excess reducing equivalents to maintain redox balance. The NADH is used in a second pathway to reduce glycerol to PDO. So we need basically 2 genes to make 2 enzymes from glycerol to take DHAP to glycerol 3-phosphate and then to glycerol with consuming 1 reducing equivalent of NADH. And then we need 2 other enzymes, glycerol dehydratase, which has 3 subunits. And it's also a coenzyme B12 dependent enzyme. It's a radical mechanism. So the cobalt B12, there's a homolytic cleavage between the cobalt and the adenosylcobalamin. That's one of the ligands. And the radical abstracts, the adenosyl radical abstracts, a hydrogen atom, which leads to dehydration to 3-hydroxypropionylaldehyde. And then you have the PDO dehydrogenase that takes a reducing equivalent and reduces the aldehyde to the alcohol. So that's our pathway from 4 enzymes that we want to introduce into our host organism. So since I believe most of you in the audience are not biochemists, I'll take a little time to do a quick primer on microbial metabolism of glucose. So this shows the glycolytic pathway of taking glucose to acetyl-CoA. And it requires a couple ATPs up front. So ATP is a source of energy to drive unfavorable reactions inside the cell. So the energy is stored in a triphosphate bond. And so it consumes 2 ATP up front to make fructose 1,6-diphosphate. And then it goes through the pathway, the glycolytic pathway down to acetyl-CoA, and it generates some ATP. It uses NADH to capture the hydrogens as reducing equivalents, and it uses ATP to capture the energy of bond breaking to use in other reactions. And if you take acetyl-CoA and feed it into the TCA cycle, then you can burn that all the way to CO2 and get more ATP and more reducing equivalents. And these intermediates all feed into a vast network of biosynthetic pathways that the cell has to produce things we're all familiar with as proteins, lipids, DNA, RNA, and to allow the cell to grow. If we do aerobic fermentations with our organism, then we get a bonus. We can take the excess reducing equivalents that we generate up in the TCA cycle and feed it into oxidative phosphorylation to make more ATP for energetic reactions. So now we want to add our pathway off of dihydroxyacetone phosphate. So now to make PDO, we're going to draw carbon out of the glycolytic pathway to PDO, and it's going to cost us a couple reducing equivalents of NADH. And if we calculate the absolute maximum theoretical yield of PDO to glucose on a weight basis, it's about 57%. So that represents on a molar basis, on a mole basis, about 2/3 of the carbon from glucose going to PDO, and only one carbon or 1/3 of the carbon going into the glycolytic pathway to support NADH generation, ATP generation, and minimal cell mass to produce PDO. So that's the high-end goal for a production organism. And if we look at that in a pie chart, what we're seeing with the host organism is that it normally is it's utilizing about 2/3 of the glucose to make biomass and about 1/3 for energy in NADH and ATP. And we're asking that same organism to only make about 10% of the glucose into biomass and half of that into energy for that biomass, and everything else goes into producing PDO. So that's a major shift that we're trying to drive this complex metabolic network that's been developed over billions of years of evolution into doing a single product. And that's for high yield. And of course, for economical fermentation, we also need to do this at high titer and high rate. So let's start. I'm going to start the story with titer. So we'll follow the titer production in our various organisms over the year from 96 to 2002. And with the initial, 4 enzymes that we've introduced into our host organism, which was in the industrial E. coli, the PDO titers we could reach were only 10 grams after a couple of years. And while native PDO producers like Klebsiella, they could produce up to 80 grams per liter PDO. So we were clearly missing something here. And so if you go, I guess we have to remember this is happening 25 years ago. So the genomics revolution of genetic engineering that we have now had not yet occurred. And doing genetics of organisms was still difficult. And so it takes time to find these genes and pull them out. So this is what many organisms do is if they have a specific pathway to go from product A, from substrate A to product B through multiple steps, in the genome, they'll often have those multiple genes together controlled by a single regulator. And that was the case for the 1,3-propane-diol production system in Klebsiella. So this was the DHA, what's called the DHA regulon in Klebsiella. And we had pulled out the DHAT and the DHA B123 to make the glycerol dehydratase and PDO dehydrogenase that was needed for the pathway. But we didn't have the knowledge at that time what some of these other genes were. The DHAR gene was known. It was a regulatory protein that helped regulate the expression of the operon or the regulon. But there was these other genes that had unknown function, and actually ORF stands for open reading frame. We have no idea what it is at that time. Again, this was 25 years ago. So the obvious thing to do was take the whole operon and put it into our production stream. And what that did was give us a step change into the amount of titer that we could produce, which matched the native PDO producers. And one of the main reasons for this was the glycerol dehydratase. Remember, glycerol dehydratase in the the engineered strain, we've treated mildly with solvents to permeabilize the cells. Basically, we're dissolving some of the lipids, not all of them, but some of the lipids, to allow movement of small molecules easily through the membrane of the E. coli. And that allows us to assay in situ specific enzymes. And we knew we had an issue with glycerol dehydratase because of the coenzyme cofactor B12. And what we saw there was the enzyme inactivated rather rapidly. It had a half-life of only 5 minutes inside the permeabilized cells. And this was due to the fact that because the adenosylcobalamin was a radical enzyme, that the radical was quenched at a relatively high frequency, so that it only do about 100,000 turnovers instead of millions of turnovers that normal enzymes do. So it had a limited lifetime due to the inactivation of the B12 coenzyme. And when we add coenzyme and ATP to the same cells, what turned out to be what the DHX and ORFX from the operon provided us was what we didn't know at the time was, but we knew later, found out later, was a reactivase. So this is an enzyme that binds to inactive glycerol dehydratase. It uses ATP to pry loose the inactive coenzyme. So it uses the energy from the hydrolysis of ATP to pull off the dead coenzyme. And now new coenzyme B12 can bind and allow activity to return. And as you can see from the chart, by doing that, by adding coenzyme and ATP in the presence of the reactivase, we can get much higher levels of 3-HPA produced. But we still knew that we weren't completely happy with the rates of glycerol dehydratase. And so we initiated a protein engineering and screening effort to try to increase enzyme stability and lower B12 requirements. I should remind you, B12 as an additive to a fermentation is quite expensive. So E. coli doesn't make B12, and it's an expensive added compound to add to a fermentation, adds to the cost. So we had a large incentive to try to reduce the B12 requirements to make the final fermentation more economical. So here where we were at in 1999 with our production strain, making PDO and glycerol. So we're at 80 grams per liter in our maximum titers with significant amounts of glycerol left behind. If we just do the simple experiment of adding no B12, so that means the glycerol dehydratase will be inactive, we can generate up to 160 or higher grams per liter of glycerol. To make an economical process, our goal was to be well over 100 grams per liter. We weren't getting there, but if we eliminate one enzyme so that we don't make the PDO, we can get to those titers. So again, something's happening here that we don't quite understand. And what we think is limiting titer is the buildup of 3-hydroxypropanol. I should mention that in NA, so this is the PDO dehydrogenase is a reversible enzyme. It goes both ways. NADH will drive the reduction of propanol. NAD will drive the oxidation of PDO back to the aldehyde. And in normal cells, try to maintain a high NAD-NADH ratio because NAD is used to capture hydrogen and electron equivalents in basic catabolic metabolism of the glycolysis. So it needs high levels NAD to capture those reducing equivalents during normal metabolism. And that's working against us because that's kind of driving higher levels of hydroxypropanol in the organism. It's known that hydroxypropanol slowly breaks down to acrolein, which is, and other toxic intermediates develop. We, at the time, we could show heat shock genes being induced at high PDO levels, but not if we leave out B12 and have high glycerol levels. And I should say heat shock genes is basically a stress indicator. So if cells, microbes are stressed by heat or by pH or chemicals, they induce these heat shock proteins that help stabilize some of the other proteins inside the cell to maintain metabolism longer. So it's a survival mechanism. So that indicated we were clearly stressing the organism through the making of 3-hydroxypropanol. So what could we do? So let me step back and kind of talk to where we were at here in 1999. So we've been working on this for 5 years. We were still way below our production goals for a viable economic organism. We've added the extra enzymes, genes, everything we thought with the regulon, the DHA regulon, 2 years ago, and we still haven't gone beyond 80 grams. The nylon business was getting nervous. They wanted to pull out of the funding and focus on the chemical route to PDO. Our managers, our biotech managers, had to go to the nylon business and convince them to give us more time, that eventually a solution would be found. And so there was a real tension there. So as a last ditch measure, we decided to better understand the inactivation due to 3-hydroxypropanol. We would knock out DHAT from our production strain. So that's the enzyme that takes 3-hydroxypropanol to PDO. So we would make only 3-hydroxypropanol. So our expectation was, this would kill the cultures. We could examine what happened inside and get an idea of how to fix it. So here's where serendipity moves in. Whoops, wrong way. What happens? When we eliminate DHAT, we get a step change in the titer. So what's going on here? So what we found through a variety of techniques is that by chance, E. coli has a set of what are called alcohol dehydrogenases. And basically then there were several unknown function. So YQHD was one of those alcohol dehydrogenases in E. coli of unknown function. Fortuitously, it worked very well of reducing 3-hydroxypropanaldehyde to PDO. So 3-HPA was a very good substrate for the gene product or the enzyme made by YQHD. And E. coli basically saved itself from death by inducing high levels of YQHD to take away the toxic 3-PA. And the other added feature was it utilized not NADH as for its reducing equivalents. It utilized a NADPH, a phosphorylated form of NAD. And cells use NADPH for anabolic reactions, namely biosynthetic reactions in the organism, because there, when you're synthesizing new molecules, you're adding reducing equivalents, and you want high levels of NADPH available. And so the ratios of reduced and oxidized NADP tend to favor the reduced form, which drives the reaction to PDO. So that was a twofold win. So let me go to the next, which I've been avoiding, which I started with but haven't talked about, is yield improvements. So the strategies for yield mainly, again, glycolysis is in the midst of this broad metabolic network, and we want to eliminate as many carbon leaks going to other compounds as possible from glycolysis, that we want to channel, and the second part is channeling as much carbon as possible to PDO. And then the third part to that is our coenzyme B12 cofactor. We need to try to enhance its production, or at least recycling it. And at that time, 25 years ago, our main methods was gene knockouts, high expression promoters, and low expression promoters to replace the native promoters. Again, promoter sits at the front of a gene in an organism genome, and it determines how much of that gene is expressed, and that determines how much enzyme you can make. And if you put in a high expression promoter, then you can make much more enzyme inside the cell. If you put in a low expression promoter, you make much lower amounts of that enzyme inside the cell. And again, E. coli was our host. It has over 4,000 genes. We went in and methodically modified over 32 of those genes on a variety of metabolic pathways to try to push the yields as high as possible. So here we are back to the glycolytic pathway with the PDO pathway added on. Our genetic modifications will be, yellow oval will be knockouts, green oval will increase levels with a high promoter, blue oval decrease with the low promoter, and protein engineering will be the red oval. So the first thing we had to do, or needed to do, was knock out PTS. So E. coli has at least 3 glucose transport systems. The PTS transport system, instead of utilizing ATP to make glucose 6-phosphate, it utilizes phosphoenophosphate. No, I got that wrong again. PEP. I'll stop there. So PEP is required to phosphorylate glucose 6-phosphate with the PTS system. If we utilize that transport system, then more than half the carbon has to go down the glycolytic pathway, and we really restrict how much can go to PDO. And then all these red arrows point to side reactions that we want to block. We want to, again, channel as much carbon in glycolysis and PDO production. And so we generated a variety of knockouts for those. And then one other, the TCA cycle here is important for generating NADH and ATP. And ARC-A is a global regulator of the TCA cycle. And it basically downregulates, reduces the levels of the enzymes in the TCA cycle under anaerobic conditions. In large-scale fermentations, there's incomplete, there's mixing, and so there's always anaerobic pockets in a large fermenter. And if an organism is in those anaerobic locations, then the TCA cycle enzymes will drop, and you'll slow down the whole process. So it was necessary to knock out this global regulator so we can maintain the TCA cycle as fast as possible. And then again, since we knocked out the PTS transport system, we had to upregulate one of the alternative transport system. This was GAL-P, that permease that transports the glucose inside the cell, and then a kinase to phosphorylate the glucose to keep it in the cell. For cofactor enhancement, again, E. coli does not make B12. It scavenges B12 from its environment, but it does have a B12 reductase that will recycle the inactive oxidized B12 to allow a conversion to the adenosylcobalamin cofactor that's needed for the glycerol dehydratase. Of course, YQHD, we didn't want to depend on the native promoter, so we added a high constitutive promoter to maintain high levels of QHD, because that's, we wanted to minimize the amount of 3-HPA in our cell since it's toxic. We also added the PP carboxylase. This is just another enzyme that helps maintain the TCA cycle by feeding more intermediates into it, and also consuming CO2 instead of sending it out as a byproduct. And then for carbon channeling, the glyceraldehyde 3-phosphate reductase, we had to, or dehydrogenase, sorry, the dehydrogenase, we had to downregulate that. Again, by downregulating this, we slow the glycolytic side of the pathway enough that more carbon will feed into the PDO side of the pathway to maximize yields. And then finally, we have the DHAB glycerol dehydratase, which we engineered to make it more stable to the inactivation with cobalt B12. And when you combine all those yield enhancements over time, we were able to get up to 51 weight percent yield, which was just above our target of 50%. So in 2002, you look at our initial production strain, we were able to achieve 135 grams per liter PDO. We had a yield of 51% gram per gram on glucose. We had a rate of 3.5 grams per liter per hour, which met the production milestones for developing a commercial organism. And of course, this was just version 1 of the production strain. As time went on and developing the pilot plant or the production plant, improved strain development continued. So this worked because we had a highly collaborative endeavor. Genencor International was paramount to make the biocatalyst successful. We had a fantastic interaction with Genencor. Tate and Lyle was absolutely needed for doing the large-scale fermentations. DuPont had, the chemical engineering expertise to do the purification of the fermentation broth to pure bio-PDO. And of course, the nylon business had all the market access and know-how in doing polymers. In 2004, we made a Tate and Lyle joint venture for bio-PDO production. In 2003, the biocatalyst team from Genencor and DuPont received the Green Chemistry Challenge Award. In 2007, DuPont, Genencor, Genencor bought Genencor in the interim time, and Tate and Lyle received the 2007 Heroes of Chemistry Award. And you see sitting Catherine Babowitz, who's the head chemical engineer for developing the process, and Charles Nakamura, who was the lead scientist for developing the biocatalyst representing DuPont. And in 2009, we got the ACS Bioderived Industrial Biotechnology Award for the entire process. So where are we at coming forward? So we have 100 million, or let me say 100 million pound facility was built in Loudon, Tennessee by Tate and Lyle. It has a significantly lower cost of manufacture than the chemical route, and it has a 50% smaller environmental footprint. It has large markets for bio-PDO applications that we talked about earlier. In 2010, 45% increased capacity announced, and in 2018, another 30% capacity expansion. In closing, I have to say this, and I think everyone in the DuPont Genencor teams would agree that this by far was the most outstanding project that any of us had ever worked on. But all good things come to an end. Of course, DuPont has been eliminating all their biotechnology businesses. They sold this business to Huifan Group, who's a major lycra producer in China just this year. And the new business name is now Covation Biomaterials, and it says they have annual sales of $250 to $300 million. Thank you.
Well, thank you very much, Mark. That was an amazing presentation. And I can say that viewing the efforts of my DuPont Central Research colleagues from afar, as well as the Tate and Lyle group, Genencor, and the other folks involved in the commercialization, we were looking at it with quite a bit of awe, bringing a masterpiece in metabolic engineering to commercialization. So at the present time, I don't see questions in chat. So I'm going to allow, okay, here's a question. Let's see. Is there a paper describing the materials and process flows? So, Mark.
You know, there's one paper on the biocatalyst development by Charlie Nakamura and Greg Whited at Genencor that was in Current Opinion Biotechnology 2003. So that is the one paper I am aware of, but the entire process, I'm not aware of anything that's in print. Have you seen anything, Keith? Because I'm
not all the materials and process flows in one place, but I noticed there are other folks from the team that are online, and if they could comment on chat, then I could relay that information to the rest of the people. Okay, there's a question. With current techniques and your experience, how long do you think it would take you to develop that process today? Yeah, and that's with the advent of things like CRISPR and genomic advances of genomic sequencing, et cetera, et cetera.
Yes. So you're talking to a biochemist, not a molecular biologist. So yeah, clearly, you know, that 10 to 11 year time span looks extremely long in today's environment of the technology and the tools available to us and all the genomics. Yeah, I don't know. I would think you could do this in some 2 to 5 year time span. It's hard, you know, part of that was serendipity, right? The YQHD discovery. I don't know, that would have to be done the way it was done. I don't think you could search for that to know it was there. I may be wrong in that, but yeah, yes, clearly with today's tools, it can go much quicker.
Right. Yeah, the YQHD especially, in being able to enjoy that serendipity is yes. I can't see how you would do it otherwise. There's another question from one of our board members, Maria Massachini. She's asking, given how good the Serona product is, how come it is only selling for $300 million annually, and how come the whole process was sold for only $240 million?
I am not a business person. I don't have the answer to that. Yes. So, in the carpet market, it's at the high end. It's not a cheap nylon carpet. It's a high-end carpet with high properties and it still has a high price. So that's limiting. Lycra, I mean, in the apparel market, it kind of competes with Lycra, add stretch. And again, Lycra is cheaper than, to my knowledge, is cheaper than Serona. So again, it has similar properties, but economics still rule. And even though it's the cheapest source of 1,3-propanediol, the Serona fiber itself is still more expensive than nylon or polyesters. So it's still, you still have to compete in economics. And so if it was the cheapest material, it would be the highest producing material, but it has very favorable properties. Applications are small enough that it doesn't. It has, by all indications, by analyses, it still has a, on the order projected 10 to 15% growth per year type of future.
Which is pretty good growth. I might add that carpet fibers that contain Serona also have some inherent stain-resistant properties. So that is a very nice feature, in addition to the stretchability that Mark mentioned. Here's another question. How much carpet fiber is sold now as Serona?
That was what, I left this business longer ago than that, almost 20 years ago. So I worked on the biocatalyst development for 6 years, and I went to other projects in early 2000s. So I haven't followed the Serona business side of things, so I don't have the answer to that. Sorry.
Yeah, sorry, I
I'm
don't
sure
either.
it's in the literature, but I just don't know what it is.
Right. There's a simple question. What does PDO stand for? I'll say it's just 1,3-propanediol, the subject of Mark's talk. There's another question. For yield as 51% gram per gram glucose, does that mean all glucose as the raw material is fed into the reactor, or just the substrate used for conversion to PDO?
No, that's all the glucose. All the glucose that's in the reactor that goes, 51% of it goes to PDO on a weight basis.
Right. And it's theoretically the most you could get is 57%, correct?
Yes.
So by my standards and what I've seen of industrial biotechnology, that is pretty darn good.
Pretty amazing. Yeah.
There's very good. There's another question. We are using green chemistry metrics. For example, E factor, process mass intensity -PMI, to evaluate our processes for active pharmaceutical ingredients, APIs. We have heard of global warming potential in equivalent CO2, but have not found a usable reference for application of GWP, global warming potential, to evaluate API synthesis. Any experience with GWP or global warming potential?
No. Yeah. Again, I'm a biochemist. I don't follow that. I would so the new business, if you want something specific around Serona, I would contact Covation Biomaterials. So Michael Salzberg is the new CEO of that business. I knew him as a business manager when we were working on PDO at back in the early 2000s. So his business has information on that. So I would, at least from the BioPDO perspective, I would try to contact Covation Biomaterials to get some sense of how they do that. But I don't.
Yeah. Okay. Thanks, Mark. And I would add that for us in industrial biotech, applied to sort of more commodity chemicals, we oftentimes do LCA life cycle analyses and use that as a potential impact on global warming. I'm sure the questionnaire, Rudy Crack has heard of that. And if you want, Rudy, you can just direct an email to me afterwards and I'll try to help you. There's another question. Is there a relatively pure carbon dioxide byproduct stream at the industrial facility? Mark, did you hear the question?
Yes, I did. I'm just trying to think the context of that question. I think the amount of CO2, right? Carbon dioxide. Yeah. I think I'm not sure. To be honest, I'm not sure. I think the amount of carbon dioxide that's generated is at levels that aren't useful to try to recapture, if that's the question. But yeah, I'm not totally familiar with the facility at Loudon that Tate and Lyle built, so I can't really answer that well.
Yeah, I can't either, Mark. Frankly, I know there's other industrial sources of CO2. I wouldn't think of this particular facility as a first option,
right,
for pure CO2 for industrial purposes. There's another question. How is the improved strain development going? The implication is strain development improvement still going on? What is the state of art for titer yield and rate for 1,3-propane-diol?
That is probably a trade secret in Covation Biomaterials. I left the project 20 years ago, so I gave you a historical perspective. I told you what happened up to 2002. I know they continued the strain improvement after that, but I wasn't involved in that research, and I don't. So to be honest, I don't know what the current rate, titer, and yields are.
Okay, that's fine.
And
I think we're approaching.
I'm pretty sure Covation treats that as a trade secret, and they probably don't divulge that information.
I would agree with you, Mark. First of all, I wanted to thank Mark and the audience for attending this very, very interesting talk. Our next talk for the Joseph Priestley Society will be on November 1st, and it's going to be on a very, very interesting topic: electric vehicles. Have we reached the tipping point? I think a lot of people in the audience will find that interesting, and hopefully your friends as well. And with that, I'd like to thank Mark Emtage, the audience, and my co-panelists, Christine and Risa, for hosting this talk, and we hope to see you at the next meeting. Thank you very much.